Okay, so just one thing I want to say, somebody sent me an email saying to post some of the classwork we did. I don't remember which specifically. I can post it all, but some of it's a mess. So yeah, I don't know. Maybe I'll just go ahead and post it all, and you guys can sort through it. But if there was something specific that you were looking for, whoever, that email got sort of buried. Just send me a reminder email. That's all. Okay, so November 22nd, we are. I did update the assignment 4 with the relevant lectures, except the last few questions are it's sort of hard to pin down what lecture they're part of because it's a combination of a bunch of techniques. And there are some hints we can give you, but I kind of want to hold back on all of the hints initially, let you think about it a little bit, because part of solving these problems is figuring out what tools to use. So I don't want to just tell you right away which tools to use in every case. But for the first few questions, I did put down which lectures. Should be pretty straightforward. And then the last few, think about it, and then if you can't figure it out, come to office hours or see a TA or something. So yeah. All right, other questions? Okay. Where I guess you still have a couple of weeks until assignment 4 is due. But yeah, it is essentially, so it's going to be all the material today and all the material next week, and then arguably, like, that would be helpful, but not necessary, right? You will have all of the tools before assignment 4 is due. This is an application of indicator random variables, but it's kind of, well, depending on what I choose to teach, it's a little more complex. So assignment 4, the rest of this, the last week is sort of material that's related to the course, but probably, I don't want to say we're not going to test you on it, but the things that we will test you on, I will let you know. Okay, we might do some graph theory stuff in the last lecture that might be relevant, but again, it's using the same techniques, but these lectures are like more advanced applications of them. So yeah, questions? Yeah. The handshaking lemma? They're way different. So the handshaking lemma has to do with the degree of each node in a graph. The crossing lemma is, if you're familiar with planar graphs, so graphs that you can draw without crossings. So you can draw in the plane, technically. You can draw in 2 dimensions. Without crossings, these are known as planar graphs. So the crossing lemma is a generalization of that. It's, well, maybe I want to draw my graph, and there's going to be some crossings. Planar graphs are great because they're less expensive, right? When I'm modeling things like, well, whatever, a highway network, right? If my 2 roads cross, then I have to have an intersection or an overpass. CPU chips, right? If I'm running lines and they intersect, now one has to be above or below the other. That increases the thickness and the cost. But sometimes we want to draw graphs with some crossings. So the crossing lemma is basically given a graph with a certain number of nodes and edges, how few crossings can I get away with?
Yeah, so that's great.
All right. All right, other questions? Okay. So yeah, today, indicator random variables. So last class, we left off talking about crazy 8s, and we didn't even quite finish calculating the first answer. So we'll get to that after today's lecture. So the nice thing about the course at this point is that I don't want to say that the hard work is done, because it's definitely not, but at a certain point, you're piling on new things, and each new thing is harder, and it's counting, and now it's counting using, Newton's binomial theorem, and then it's, then it's recursion, which is really nasty, and then it's probability, which is like, okay, I mean, I'm reusing counting, so that's not so bad. And then random variables and independent random variables, and that's a pain. But then you get to expected value, and things are easier. And then you get to indicator random variables, and things get way easier if you use them correctly, right? So this is sort of the nice part of the course where it's, wow, it's amazing how well these tools work. So yeah, that's what we're going to look at today is indicator random variables. Okay, so as a review, of course, so what we took when we took infinite sample spaces, that's technically an example of a geometric distribution, right? If I look at the probability function and I sort of plot out all of the probabilities on a graph, the graph would look something like this, right? So where this is my probability is the y-axis, and the number of trials is the x-axis. That's sort of how the geometric distribution looks. And then if you sum it all up, sum up the area under the curve, you sum to 1. So yeah, that is, I think I'm missing some words up here, but that is the idea that I perform an experiment and I get success with probability P and failure with probability 1 minus P. And I keep performing the experiment until I succeed. Okay, and that gives me a geometric distribution of these probabilities. So, and what we learned is that if I define a random variable x, where x is the number of trials until I succeed, then the expected value of x is 1 over the probability, right? So for a fair coin, if you asked on average how many times would I have to flip it until it comes up heads for the first time, that would be 1 over 1/2. If it's a fair coin, which would be 2. And this is a nice result, easy to apply. And yeah, okay, I did exactly this example. Another example, if you play the lottery each week with a probability P of winning the jackpot, 1 in 1 million, right? So it is even possible to have a lottery where your expected winnings are positive, but the amount of time it's going to take you to win is so big that you're going to lose, right? So if, for instance, I have the lottery, I play it each week, and the probability is 1 in 1 million of winning, then my expected number of weeks until I win the jackpot is 1 million, right? So on average, that's how long it would take me to win the jackpot. If I happen to live that long, I could definitely win the jackpot, but you know, probably I'd be dead before 1 million weeks is up. Okay, so we're going to talk about, on our way to talk about indicator random variables, we'll also talk about, again, we're going to touch on Newton's binomial theorem and or the binomial distribution, right? So this sort of, we'll get into exactly what they are. So in this case, I have a similar thing, but I'm not going to go until I succeed. I'm going to flip my coin n times, and we'll say that it comes up heads with probability P and tails with probability 1 minus P. And of course, P is somewhere between 0 and 1. So each individual coin flip, you know, I have 2 possible outcomes. But if I do it n times, then I want to know the expected number of times it's going to come up heads. So we will define a random variable x to be the number of times it comes up heads. And we want to find the expected value of x. So we're going to do it the really hard way, but sort of, it is a useful exercise in that we are going to review the binomial distribution. And then once we're done the really hard way, we're going to solve it with indicator random variables and see how easy it can be. Okay, so yes, let's say I flip my coin 4 times and it comes up heads once, then x would take on the value of 1. All right, so yeah, Yeah, what would our intuition be? So I flipped the coin 10 times. It's a fair coin. How many times on average would I expect to see heads? Yeah, yeah, it's going to be about half. Well, on average, if you did it, as you increase the number of trials, it would converge to 1/2. And in general, this applies to n, right? So whether it's 10 coins or 100 coins or 1,000,000 coins, on average, I would expect to see half of them be heads. If the coin was not fair and it came up heads with probability 1/3, then I would expect to see about 1/3 of those coins to be heads. So my expected value of X would be about 1/3 n. That's our intuition. And it's a good intuition, and we're going to prove that it's correct. Yeah. Okay. So this is the question we're posing. Is our intuition correct? Is the expected value of X going to be the probability that I get heads times the number of coins? So we're going to use our good old-fashioned tools. We're going to iterate over the range of X. Right? So we're going to use this definition of expected value and then look at all of the possibilities for K. So what are the possibilities for K? Well, I could have 0 heads, right? Every coin flip can come up tails, or I can have all n of them be heads, and any number in between. So this summation here, K is going to take on the values from 0 to n. Okay. And my sample space is going to look something like this. So if I have n coin flips, then a given outcome would be some, n coin flips where some number are heads and the remaining ones are tails. Okay, so let's sort of expand this out and look at the terms and see how we can compute their probability. Not just their probability, but the value K times the probability that X is equal to K. So essentially, we remember that we can use our random variables to define events. So an event is just a collection of outcomes. So if we looked at, say we flipped our coin 4 times, and then the event is that 2 heads, we flipped heads twice. So we want to, just as an example, we're going to find the probability of this and basically what this term looks like. Okay, so we have an event, 2 heads were flipped. And if we look at the subset of all possible outcomes, right? So remember n is equal to 4, so we flipped 4 coins. And these are, we can just basically iterate them. There's 6 of them. And these are all the outcomes where I flipped heads twice. Okay, so now we want to find the probability of this event. So what is the probability that X is equal to 2 when n is equal to 4? The trick is that if this was a uniform probability space, then of course I could take the size of the sample space as the denominator and the size of this event as the numerator. But I don't know that it's a uniform sample space because P might not be, if P was a half, then it's a uniform sample space. But if P is any other number, then it's not. Right? So then different outcomes are going to have different probabilities. So we can't just use the old-fashioned method, or sorry, the counting method. We have to actually iterate these out a little bit. So let's take a look at this example and look at the individual outcomes and look at the probability of each of those individual outcomes. So yeah, one of my outcomes is, well, the first 2 coin flips are heads, the second 2 are tails, and each of those coin flips is independent, and it comes up heads with probability P and tails with probability 1 minus P. And because they're independent, then the probability that all of these things happen is equal to the product of the probability, right? This is simply probability HHTT I mean, I really should have put probability here. But this is just probability of heads times probability of heads times probability of tails times probability of tails, because these are independent. So that's sort of what I'm demonstrating here. All right. So the next, we have 6 outcomes. The next one, heads, tails, heads, tails. Well, again, each head comes up with probability P. Each tail comes up with probability 1 minus P. So the probability of this outcome looks something like this. This is, first coin is heads, second coin is tails, first coin or third coin is heads, fourth coin is tails. And I could keep going. Heads, tails, tails, heads. That's of course P times 1 minus P times 1 minus P times P. And tails, heads, heads, tails. That looks like that. And so on and so forth. Okay. So these are all of the outcomes in my event, and these are all of the probabilities associated with those outcomes. And so to find the probability that x is equal to 2, I would sum these up. Okay, but I know something about multiplication. I know it is commutative. So I can actually rewrite each of these, right? I can note that P occurs twice in each of them, and 1 minus P occurs twice in each of them. So that means that if I rearrange the terms, I can write them all, and I see that even though it's not a uniform sample space, in this event, all of the outcomes have the same probability. Okay. Well, that's good because now I can simplify my expression. Again, I'm trying to find the probability that x is equal to 2. I have all of these outcomes in my event, and now I simply sum them up. That's the definition of the probability of an event. There's 6 of them, so I could write it as 6 times p squared 1 minus p squared, right? But really what we did with this 6 is, I mean, we counted it explicitly. But another way to get it is to say, well, there's 4 coins that I flipped, and I'm going to choose 2 of those to be heads, right? So the number of possible arrangements where 2 coins are heads is 4 choose 2. Right? So that, when I say this is equal to 6, that is actually equal to 4 choose 2, which is 6. Okay. Questions so far? Okay. So yes, we want to find the value of the expected value of x, and to do that, we're going to have to find all of these individual probabilities. We looked at the probability that x is equal to 2, and we determined that it is 4 choose 2 p squared 1 minus p squared. So we're on our way now. We just have to generalize that for any n and k. Okay, so yeah, we want to generalize this, and then we could plug that into our equation and then maybe get something useful. So in general, if I have, this is my n, where this is the number of coin flips, and this is my k, which is the number that come up heads. So in my general formula, I would say that, well, the number of outcomes from n coins and k come up heads is n choose k. And then the probability, well, if k of them come up heads, each of those has the probability p of coming up, right? And because these are independent, we can multiply them all out. And because they're commutative, we can rearrange the terms. And the same thing, if I have k heads out of n, then I have n minus k tails. And these have a probability of 1 minus p. So each individual outcome has this probability, and there are n choose k of those outcomes. Okay, so my general formula for this event, x equals k, is n choose k p to the power k, 1 minus p to the n minus k. And this sort of looks like, starting to look sort of like this. Okay, questions? All right. All right. However, that's not really what our formula is. So we know this is what we want to compute. We know the probability of each individual term is this. So when I write out my expected value of x, I actually get this k times n choose k, p to the power k, 1 minus p to the n minus k. And that is almost Newton's binomial theorem, but not quite, because I have this k here that I don't have in Newton's binomial theorem. So I don't have a closed form for this. It would have been nice. I could have used this, but I don't quite have it. So to get a closed form for this summation, we're going to do the same thing we did for the geometric distribution, right? We had a summation there as well. And we wanted to, so we had, just as a reminder, we had this, what was it? X equals 0 to infinity of, I equals 0 to infinity of x to the I. And that is 1 over 1 minus x. And then when we did expected value, we had this same thing. I equals 0 to infinity of I times x I minus 1. And then, so to find a closed form for that, we took the derivative, right? And that worked out to this. So we're going to do the same thing for this. We're going to, as it turns out, we can just use the same trick again. We can take the derivative of this expression. We just have to figure out the right thing to take the derivative of with respect to. Okay, so yeah, if we take out the k, it looks like Newton. So we want to take Newtons, and we want to introduce this k. And if I wanted to take the derivative of this and introduce a constant k, or sorry, a term, or a k, a factor of k, then it looks like I can take the derivative with respect to y, as we will see. Okay, so yeah, this is what we want to show, but this is the tool that we presently have. And if we take the derivative with respect to y, then, well, this is simply some number times y to the power k. And if I take the derivative of that, I get k times some number x n minus k times y to the k minus 1. Right? That's the derivative with respect to y of any of these individual terms is going to be this. Okay, so if we do that, we get an expression that is starting to look more like what we want. We've introduced this k here. And, x is, I've kind of written it backwards, but x and y are sort of interchangeable. So I have an x to my n minus k times, this is p to the k, but this is y to the k minus 1. So it's not quite the same, but we're getting pretty close. And if I take the left-hand side of this and I take the derivative with respect to y, then I get, right, so I bring down the n in front, and I get n times x plus y to the n minus 1. Okay, so we have a closed form for this, but this is not quite what we're trying to solve. So let's now introduce a term to make it look like this. Okay, so this is what we have so far. We want, we have y to the k minus 1. We kind of want a y to the k, right? Because if I substituted y in for p and x in for 1 minus p, then this would be almost this, except for this k minus 1. So I'm just going to multiply the right-hand side by y and the left-hand side by y, right? So if I multiply the right-hand side by y, then I'm just going to distribute y across all the terms. So it's going to, each of these is going to be multiplied by y. And if I multiply by y, then I'm going to basically raise y to one more power, right? So then I get this, I get y to the power k, and I multiply the left-hand side by y as well, and I just get n times y, x plus y to the n minus 1. Not super pretty at this point, but it's a closed form. We can work with it. So yeah, now we have basically what we're looking for here, right? It has the same form with, if I substitute p for y and 1 minus p for x, and I have a closed form for it by taking the derivative. Same trick as we used before. Okay, questions? All right. Okay, so now we have another tool in our toolbox. We still want to solve our original problem, which is this. The expected value of x we determined to be this expression. I have now this, which looks the same if I substitute x and y with p and 1 minus p, right? So this is my closed form, so I'm going to sort of, as an intermediate step, write that down and then say, well, which of these is p and which is 1 minus p? Well, we'll set x equal to 1 minus p and y equal to p in this closed form, and we get n times p times 1 minus p plus p. The p's, of course, cancel out. All of that to the power of n minus 1. Once the p's cancel out, I just have 1 raised to the n minus 1, which is always going to be 1. And I have n times p remaining. Okay, so we went through a lot of steps. Our guess was that the expected value of x was equal to the probability that, so the expected number of heads is equal to the probability that heads comes up times the total number of coin flips. And we've proven it. Using a very, very difficult, laborious method, but a nice little review of binomial distribution and Newton's binomial theorem. Questions? Okay. So as promised, there's an easier way to do this. So what I'm going to do is I'm going to make a bunch of new random variables. So x1 through xn, and these are going to be very, very simple. They're going to take on a value of 1 if the ith coin flip is heads, and 0 if the ith coin flip is tails, right? So I have, my previous example, if I flipped 4 coins and I had x1, x2, x3, x4, and if I have something that looks like this, then x1 equals 1, x2 equals 0, x3 equals 0, and x4 equals 1. Okay, so these are my indicator random variables, and if I do that, then the number of times I flip heads is simply the sum, right? So I flipped heads once in the beginning and once in the end, and these two are 0, so if I added those up, I get 2, and I flipped exactly 2 coins to be heads, right? So I can express my random variable x as the sum of these other random variables. And since we have, we know that we can use the linearity of expectation. So the expected value of x is equal to the expected value of this sum. And using linearity of expectation, that means it's equal to the sum of these expected values. Okay, so I have, in this case, n random variables, and I'm going to sum up all of their expected values. Okay, so I need to figure out what is the expected value of xi. again, I'm going to use this formula for expected value. I'm going to sum over the range, but we're going to see something interesting here. If I expand that out, k can take on the values 1 or 0, right? So this is all possible values that my random variable can take. So those are the only two terms if I expand this out, which means that my expected value of xi is equal to 0 times whatever this is. Well, I don't care, it's 0. Plus 1 times the probability that xi is equal to 1. So that means that 0 term drops out. And for an indicator random variable, or for a random variable with this form, my expected value is simply equal to the probability that it's 1. And what is the probability that it's 1? Well, it's the probability that the ith coin flip is heads. So indicator random variables are simply the expected value is equal to the probability of the event I'm trying to indicate. Right? So in this case, this is, ith coin flip is heads. Okay. I know that I flip my coin and it has probability P of coming up heads, probability 1 minus P of coming up tails. These are independent coin flips. So the probability of this event is P, which means that my expected value of xi is also P. Again, very, very simple. So I know the expected value of these indicator random variables, these variables that are indicating whether this flip was heads or tails. And I know, right, previously I determined that my expected value of x is equal to the sum of the expected values. So each of these has the same probability P, and I have n of them. So when I add them up, I get n times P. Okay, so yeah, these are known as indicator random variables because they indicate whether something is going to happen or not. I want to count some event. For instance, how many times I flip heads out of n coin flips. Then I define a random variable that takes on two values, 1 or 0. And the nice part about that is that the expected value of these are very simple to compute. It's simply the probability of this event. Okay, and then using that in conjunction with linearity of expectation, you can solve some problems very, very easily. Right? So we got the same solution as we did before using this really clunky method. But yeah, now it's really, really easy. All right, questions? Let's try and solve another problem or just crash. All right. Okay, so we're going to no. All right, so we're going to look at another problem, and we're going to use indicator random variables to solve it. And this is going to reveal another interesting property of indicator random variables. All right, so I'm going to look at a random bit string. Right, so again, bit strings are just strings of zeros and ones. And random, well, if they're uniformly random, then all of these possible bit strings have an equal probability of coming up. But even if it's not a random bit string, I can define a bit string and I can define a block in a bit string as a number of consecutive ones. Right? So in this case, I would have one block here, since it's a substring of consecutive ones, and it has 0 on either side. I have another block here. It's a substring of consecutive ones. And I have another block here, also a substring of consecutive ones. Doesn't necessarily have to have 0 on either side. It can just have nothing, as in this case. Okay, so this bit string has 3 blocks of ones. And so yeah, we've defined a block as a maximal contiguous subsequence of ones in our bit string. Maximal means that right? This technically does not count as a block since I can make a bigger block using those same bits. So it has to be maximal. And given random bit strings of length n, so these are uniformly random bit strings, which implies a couple things. And one of them is that each bit is a 0 with probability 1/2 and a 1 with probability 1/2. It also implies that every unique bit string comes up with the same probability. So given this definition of random bit string, I want to know the number of blocks, or more specifically, I want to know on average how many blocks could I expect. So in this example, my random variable x has a value 3 because there are 1, 2, 3 blocks of ones. So yeah, the problem now is, what is my expected number of blocks? Okay. All right. So how can we compute it? Well, again, we could try the old-fashioned way where we take we iterate over k times the probability that x is equal to k, right? We could try and use this, but let's take a look at what that might look like. All possible values of k. So the fewest number of blocks is, of course, 0, right? I have no ones at all, so k is equal to 0. The most number of blocks I could have is, if every second number was a 1, basically. And then that's give or take 1 bit. Right, so the largest possible number of blocks is the ceiling of n/2, right? So I can start with a 1, and then maybe I end with a 1. But if I have an even number, then I end with a 0, or a 1, actually, it doesn't matter. So that's the largest possible number of blocks, which means that if I'm iterating over the range, I'm going to iterate from k equals 0 to the ceiling of n/2. And like before, we would need to figure out this probability. So what's the probability that I have exactly k blocks? Let's say, what's the probability that I have exactly 3 blocks on some value n? Well, if I have, I don't know how many bits are there, but however many bits there are, if I look at all of the ways I could have 3 blocks, well, here's one. Here's another. This also has 3 blocks. And here's another one. This one has 3 blocks. So there's not really a pattern there I can sort of count easily, right? There's a lot of different ways that I can have 3 blocks. Possibly you could count them. Maybe that's a good assignment question. So yeah, trying to count bit strings of length n with exactly 3 blocks, it seems like a lot of work. So let's of course do it the easy way. Let's use our new tools, our indicator random variables. Okay, so we're going to, when we look at the problem, we notice that each block has a leftmost 1, right? It's a contiguous subsequence of 1s. There has to be a leftmost 1, and to the left of that is either a 0, or maybe if this is a 1, there's nothing over here, right? So empty set, not 0. Yeah, so this block also has a leftmost bit, and this block also has a leftmost bit. So any consecutive subsequence of 1s has a leftmost 1 in our bit string. So instead of explicitly counting the blocks, we can use indicator random variables and count how many of these leftmost 1s exist. Right, so I'm going to use indicator random variables, xi, 1 for each of these positions. And this indicator random variable would be 1 if a block starts at I, if this is the leftmost 1 in a block, or 0 otherwise. Okay, and the fact that, this is maybe an awkward definition doesn't really matter in terms of random variables, as long as mathematically it works. So I can say, well, in our above example, if I look at all of the indicator random variables, then 3 of them are 1s. This is x1 is 0, x2 is equal to 1, x3 is 0, x4 is equal to 1, x5 is 0, right, because it does not start a block, and so on and so forth. So if I sum up these indicator random variables, I will get the number of blocks. And in this case, each of these indicates, the start of a block. So x is equal to 3. All right. Good. So everybody understand the problem? Any questions? Okay. So x is equal to the sum of these indicator random variables. I want to find the expected value of x. Well, I can use linearity of expectation. So now this is equal to the sum of all of these, or the sum of the expected values of all these indicator random variables. So now it's left to find, well, these are indicator random variables, right? So we know that the expected value is equal to this, but this cancels out. So it's 1 times the probability that it's equal to 1, which is simply the probability of whatever I'm trying to indicate. So it's the probability that this bit is the leftmost bit in a subsequence of 1s. Okay, so let's determine this. So what has to be true? Well, we'll look at 2 different cases, right? So sometimes I know that this starts a block because the bit to the left is a 0. And this bit is a 1. Right? So both of these things have to be true. For this one, for x4 to be equal to 1, I need that I basically need that bit 3 is a 0 and bit 4 is a 1. Okay, so that's the first case we will look at. And then the other case is, well, I sort of have a special case here. If this is a 1, then that's it. It starts a subsequence. So there's nothing to the left of it, so I only have to look at this bit to know whether or not it starts a subsequence. So we have 2 separate cases. Either I'm looking at the first location, or I'm looking at anywhere else. Okay, so if I'm looking anywhere but the first location, well then this is the start of a block, xi is equal to 1, that's the same thing. If, for instance, if I'm x4 is equal to 1, if this is a 1 and this is a 0. So, yeah, basically like that. So now I want the probability that this can happen. This is a random bit string. That means this comes up 0 with probability 1/2, and this comes up 1 with probability 1/2. So the probability that my left bit is a 0 and I'm a 1 is 1/4. Okay. So easy enough. Yeah. On the other hand, if I'm at the beginning, right, if I'm looking at bit 1, then it only matters if bit 1 is a 1. If it's a 1, then this is the start, the leftmost bit of a block of 1s. And if it's a 0, it's not. So x1 is equal to 1 if and only if the first bit is a 1. And it's a random bit string, so the probability that the first bit is a 1 is 1/2. Okay, and that's it. Yeah. I now have the expected value of all of my indicator random variables. So when I plug these in, I get, well, this is probability 1/2, and all of the rest of these are probability 1/4. Right? So this is 1/4 added to itself n minus 1 times, plus 1/2, and then I do some algebra, and I get n plus 1 over 4. Okay, so the expected number of blocks contiguous subsequences of ones on average is going to be about a quarter of whatever n is. All right. Questions? Okay, so what's significant about this? Well, we know random variables, and we know this idea about what if whether random variables are independent or not. Right, so let's say that I knew that x2 was equal to 1. Does that give me any information? So I determine the probability, right? But individually. But what if I know that x2 is equal to 1? What does that tell me about x3? So x2 equal to 1. Well, let's say, let's take an example that we actually have. x4 is equal to 1. So what can I say about x5? And what can I say about x3? Yeah. Yeah, this must be 0, and this must be 0 as well. This is not the bit value. This is this the start, the leftmost bit of a subsequence of 1s? Well, it can't be, because 4 is the leftmost bit. So whether this is a 1 or a 0, it can't start a new subsequence. Also, I know if 4 is a 1 and it's the leftmost bit in a subsequence, then this must be 0. Right, so this also cannot start a new substring of 1s. So what does that tell us? That tells us these are not independent random variables. Right, so how can I possibly say something about the value of x2 without taking into consideration the value of x3 and x1? Well, I mean, it turns out that these are not independent random variables. It also turns out that that doesn't matter, right? As weird as that sounds, I can look at them all individually. I can determine their expected value individually and not have to worry about the dependencies between random variables. And the reason for that is because when we did the definition of the linearity of expectation, we didn't use the fact that they were independent. We didn't care if they were independent or not. We just used the definition of expected value. Right? So even though these are not independent random variables, we can still use indicator random variables and linearity of expectation to solve these problems, which means that we solve a lot of problems. All right. Questions? Okay. So yeah, this is a short one. So we will go back to our problem from yesterday, and then we'll look at some other problems as well. But yeah, our problem from yesterday was here. And yeah, it might be worth reviewing it. So what we're doing is we are playing crazy eights with a standard deck of 52 cards. Every player gets a hand of 5 cards, and then eights are wild. So we want to figure out the expected number of eights in our hand. Right? And we have 52 cards. This consists of 13 ranks, ace through king, and each of those ranks has 4 suits: spades, diamonds, clubs, hearts. So that makes 52. So the question asks us to find the expected number of eights in our hand 3 different ways. And we're going to see basically how much easier it is to solve the problem if you just choose the right random variables. So we're going to start just by not choosing any random variables. We're just going to use the probability, the expected value definition of summing over the range. So what that means is that, well, K, I know, represents the number of eights in my hand of 5 cards. And there are 4 eights in total. So I can have anywhere from 0 eights up to 4 eights in my hand. So if I expand out this, I get, let me erase this and redraw it. Okay, so if I expand out that summation, I get this formula with a couple extra ticks. But I have 0 times the probability that x is equal to 0 plus 1 times the probability that x is equal to 1. Et cetera, et cetera. Okay, and then we wanted to basically find the expected value of x. So when we started, we started by just determining the probabilities. So what we did is said, well, each hand is dealt uniformly at random. So this is a uniform probability space. So we can reduce it to counting. So it's the size of, so how many hands do I have with exactly 1 8 in them over the total number of hands possible? Okay, so how many hands do I have with exactly 1 8? Well, I'm going to use the product rule. I choose an 8 out of the 4 available. So this is 4, or let's write it as 4, choose 1. And then I have 4 other cards that I can choose. I know they're not 8s. So that means instead of 52 cards, I'm choosing out of 48, and I'm choosing 4 cards. And yeah, using the product rule, 4 choose 1 times 48 choose 4 over 52 choose 5. That is for the probability that I have exactly 1 8 in my hand. Okay, and then I just do the same thing, and you start to see a pattern emerge. So the probability that I have exactly 2 8s in my hand, well, I have 4 8s to choose from. I will choose 2 of them. And then I have 3 additional cards in my hand of 5. And I have 48 other cards that are not 8s. So I'm going to choose 3 of those. And again, over 52, choose 5. If I have 3 8s, then again, 4 8s, and I'm choosing 3. And then I have only 2 cards left over to choose from the 48 cards that are not 8s. And then if I choose 4 8s, or if I have 4 8s in my hand, well, 4 choose 4. I had 4 8s. I chose 4 of them. That's also equal to 1. And then I have 1 additional card to choose from the 48 remaining. I'm going to keep them in their binomial coefficient form, even though I could simplify some of these, right? This is just 1 times 48, which is 48. That's pretty easy to see, hopefully. But I'm going to keep it in this form because I'm not going to compute this. It's ridiculous. I'm going to plug it into Wolfram Alpha and see what we get. Okay, so these are all of the individual probabilities, and they do kind of follow a pattern. So we can, and we also have to multiply them times their K value. Of course, this is 0, so we can skip that. All right, interesting. Okay, so this is our formula, and so expected value of x is equal to, I'm going to write this as a sum, and since we're ignoring the first one, since we're ignoring k equals to 0 because that is just 0, we're going to take k equals 1 to 4. And then if I look at the pattern, well, the pattern is 4 choose k, and then 48 choose 5 minus k, all over 52 choose 5.
This, you assume it's like here.
Okay. So ugly, 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 but we can come up with a nice succinct way to express it. There might be an easy way to cancel all this stuff out, but I'm not even going to bother to try. Or should I? No, it's probably too much of a pain. I'm just going to plug it into Wolfram Alpha, see what we get. Questions so far? Okay. So Wolfram Alpha is nice. I can actually do stuff like this. If I remember what the formula is, I'll do sum. I always sort of, it understands LaTeX, so I sort of default to LaTeX, but it can also mix and match things. K equals 1 to 4. So that's that summation. And now I have to be careful of the brackets. Yeah, so 4, choose K times 48, choose 5 minus K, and all of that over 52, choose 5. Okay. And I need one more bracket. Okay, good. So this is what we had written. Hopefully. Nope, I messed it up. Okay. We'll choose K. Oh, yes. What did I forget? So this is a nice formula, but this is just the sum of the probabilities. I forgot to multiply, right? I want the expected value, so it's K times these probabilities. So I forgot to multiply by K. So this is, what can I do? Maybe let's put it in here. Probably that'll work. K times that. Okay, so that's, look at that. 5 over 13. Whew, I didn't have to do that myself. That would have been a mess. Yeah. So yeah, Wolfram Alpha is great for stuff like this. But, questions? Okay, so I know what the answer is now, or at least I suspect this is the right answer. I know what's the right answer, but so this is equal to 5 over 13. Really, there might be a way to simplify it, but it looked pretty nasty. I didn't really want to try. So the next thing I'm going to do is I'm going to define indicator random variables. And so yeah, we're going to number each individual 8 by suit, right? So I'm going to give, so spades will be 1, diamonds will be 2, clubs will be 3, hearts will be 4, and then I'll define these indicator random variables. I also could have done subscript for those, I guess, but so, AI is that the 8 of whatever that suit is in your hand. So AI is equal to 1 if that 8 is in your hand and 0 otherwise. So basically, I have indicator random variables for each 8. Okay. So so now my expected value of X is equal to, well, how many 8s? Or let's start with X is equal to A1 plus A2 plus A3 plus A4, right? These are equal to 1 if that particular 8 is in my hand, and each of them corresponds to some suit. So now my expected value of X is the expected value, the sum of the expected values of each of these because of the linearity of expectation. Okay, so now I have, and these are symmetric, right? There's really no difference between the 8 of hearts and the 8 of spades in terms of its probability of being in my hand. It's exactly the same. So I can determine an individual probability. So let's say, doesn't matter, I'll say AI. This is an indicator random variable. If I summed over the range, I guess let's be a little bit explicit a few more times, and then I will start to leave this part out. Right, so that is the expected value of this indicator, which is simply equal to the probability that that 8 is in my hand. So what is the probability that that 8 is in my hand? Okay, well, it's a uniform probability space, right? So this is just a counting question. So probability that AI equals 1, or the 8 of I is equal to, is in my hand. Well, it's all the hands that have that 8 over the sample space. So how many hands have, let's say, let's make it explicit, the 8 of, what's the easiest thing to draw? Oh goodness, heart, I guess. I can't draw anything, so. And this, it looks like the ace of hearts. It should be the 8 of hearts. This is, anyway, whatever. So what is the number of hands I have that have the 8 of hearts in them? Well, I can use the product rule, right? Anybody have any idea how I would calculate that? Yeah. Exactly. Everybody see how we got there? So I know I have that it's the 8 of hearts. I know that's in my hand. I have one way to choose that. Right? And then I have, well, I don't care about the other 8s at this point. Right? I have 51 other cards, and I need to choose 4 of them to complete my hand of 5 cards. So 51, choose 4, and all of that is, of course, over 52, choose 5. And that is the same probability for each of the 8s. Okay, so this is a little bit ugly, but not quite as ugly as what we had before. So let's see if we can do this by hand. So this is, again, these are symmetric. So this is the same probability. This is 51 factorial over, and please let me know if I mess up. That is 51, choose 4, and then 52, choose 5 is 47 factorial over 5 factorial. Okay, and then I'll invert and multiply. So this is equal to 51 factorial, 47 factorial, 4 factorial, times 47 factorial, 5 factorial over 52 factorial. Great, this cancels out. This cancels out except for this factor of 52. And this cancels out except for this factor of 5. So this is 5 over 52. Okay. Questions so far? All right. Not quite as bad as the other one. Not great. But now my expected value of x is equal to the sum of 4 of these. Right, so if I rewrite that, ex equals, let's just write it as 1 to 4. No, sorry. Yeah, I could do that, I guess. It doesn't matter. So let's just write it out. A1 plus A2 plus A3 plus A4. These are all the same. These are all 5 over 52. Etc. That is equal to 4 times 5 over 52, which is equal to 20 over 52. And if you divide that by 4, you get 5 over 13. Okay. That's same answer, slightly easier using indicator random variables. Questions? Okay. Well, let's be even smarter about how we choose our indicator random variables. Yeah. Yeah. Awesome. That sounds. So it's about what?
identify of my own about 0.84.
384?
Yeah.
Okay, so about 38%.
Yeah.
That's not 30, sorry. Yeah, no, that's the expected. So that's, yeah, it is, it works out this probability of any individual weight. Okay. All right, so now finally we're going to do these expected, these random variables, these indicator random variables. Ci is equal to 1 if my ith card is an 8 and 0 otherwise. So now if I want to express x, each of these represents the card number in my hand. And if it's an 8, that is equal to 1. And if it's not an 8, it's equal to 0. Okay, so then, of course, my expected value of x is equal to C1 plus the expected value of C5. So just the linearity of expectation, the sum of the expected values. And again, it's symmetric, right? Yeah. Yeah, we could write it like that. Yeah, I'm trying to use as little notation as I can. Okay. Yeah, you think so? Okay, for some people it does. All right, so let's figure out the expected value of any individual card. Of course, this is an indicator random variable, so this is simply the probability that it's equal to 1, which is the probability that that card is an 8. Okay, so what is the probability that that card is an 8? Well, we can actually cheat a little bit. Instead of counting all of the hands, we can say, well, this is a uniform probability space, so each of these cards basically is chosen uniformly at random from our deck of 52, right? It's equally likely, this C1 is equally likely to be any one of the 52 cards in the deck. And the same with C2 and the same with C3. So what I'm really asking is that I have one card separate from, I don't care about the rest of my hand now. Is it an 8? I pull one card from the deck, do I get an 8? So what's the probability of that? Well, that is basically now I'm thinking of, I reduce my probability space to a hand of one card. So I have, of course, my sample space is 52 choices. And out of those, 4 of them are 8s. Right? And this is 1 over 13. Okay, so now my expected value of x, I have 5 cards, and each one has probability of 1 over 13 of being an 8. So my expected value of x is equal to 1 over 13 plus 1 over 13 5 times, which is equal to 5 over 13. So it's the exact same answer, but way, way, way easier to compute, right? Just by choice of how I approach the problem, and specifically choice of indicator random variables in this case. Indicator random variables are not always useful depending on the problem, but if they are, then they are usually the easiest way. All right, questions? Yeah. So I use the idea that, so I sort of cheated, right? Because I said that each card is dealt uniformly at random. So if I have a collection of 5 cards, in some sense, there is a sorry, I just want to get the wording correct. Well, okay, I'm just going to sort of bludgeon it maybe. Each of those cards, if I'm dealt 5 cards, uniformly at random, then each one of those is individually equally likely to be any of the cards in their deck. So I did in fact use the product tool, but I didn't have anything to multiply, right? So I reduced my probability space to now I'm just looking at one individual card that I've been dealt. And it could be any, with equal probability, any of the 52 cards. So now my sample space is simply 52 choices. And is it an 8? So I'm technically using the product rule in this case. So I'm choosing, I want to count the number of ways that this card could be an 8, and there's 4 ways. But I have no second task. That's it. I just have one task. That's why we didn't use the product rule. Yeah. Other questions? Okay. What we got? 9 minutes left. It's always an awkward amount of time for something like this. This one, I really like this one. This one's cool, but it's going to take too long. We can try and do this one. This probably we have just enough time. So in terms of expected value and payout, I guess this would be good practice for some of the money questions. So Lindsay and Simon are playing a game, and the expected amount of money that each of them wins. Yeah, they want to play a game where they have an equal chance, right? So they want to make some rules, but they want to make sure that whatever their return is, they're equally likely to win or lose. So their expected winnings are 0. So, yeah. So the game is this. Lindsay rolls a fair die independently 3 times. If none of the 3 rolls results in 6, then Lindsay pays $1 to Simon. If exactly one of the rolls is 6, then Simon pays $1 to Lindsay. And if exactly 2 of rolls result in 6, Simon pays $2. And if all 3 result in 6, then Simon pays X dollars. So we want to find an X so that the expected winnings are 0, right? So that after the game, they're probably going to go home with all their money, but no extra. Okay, so let's say that X equals Simon's winnings. First of all, does any questions on the problem, or does everybody understand? Okay, so we want, maybe not X. Let's make, maybe not S, maybe make it what? So this indicator, or this random variable Y, is equal to Simon's winnings. I want to find an X that makes Y equal to, or the expected value of Y equal to 0. This is my goal, given this game and the probabilities. Okay, so my expected value of Y, I'm going to use this, the K times the probability that Y is equal to K. So let's look at all the possible values. Yeah, so this is the expected winnings over one game, right? So Y, you could define it for multiple games, they just use linearity of expectation. It's the exact same thing. So Y is Simon's winnings on average for playing one round of this game. So the outcomes are, well, in the first case, if none of the 3 rolls is a 6, Lindsay pays $1. So this is 1 times Y equals 1 over the sample space. Our sample space is, we're rolling 3 dice, right? So every time we roll 3 dice, so this is going to be 6 to the power 3. Okay, so that's the size, and Y equals 1 is, well, we'll get to that. Plus, all right, so yeah, plus, Simon pays $1 to Lindsay. That is -1 if one of the rolls results in 6. Okay, let's write this like this. No sixes. 1, 6. Okay, so -1 is the payout if there's exactly 1, 6, and it's the size of 1, 6. Plus, in this case, Simon loses $2, so -2, and this is 2 6s over 6 cubed, and then all 3 is x 3 6s. Maybe I won't have time to get through this. I don't know. Okay, so that's our expected value of y, and we want to find a value for x that makes all of this equal 0. Okay, so the number of ways I can roll no sixes on 3 dice is, anybody quickly? Yeah, so this is equal to 5 to the power 3 over 6 to the power 3. That's for this guy. 1 6. Well, that's, I have 3 dice. I choose one of them to be a 6. There's 3 ways to do that, times then 5 ways to roll the, 5 ways to roll a 1 through 5 on each of the other 2 dice. Plus -2, 2 6s. Well, that is 3, choose 2. And then times 5 for the remaining die. And all 3 6s is x times, well, there's one way to do that, right? Okay. So that's my expected value of y. And, oh boy, can I quickly compute this? So 5, 3, 125 over, what is 6 to the 3? I don't know. Anyway, 6 to the 3. It's all over 6 to the 3, so minus 75 for the second term here, minus 1530 plus x. And basically we want that to be 0. So it doesn't really matter what 6 to the 3 is. So 125 minus 75 is 50, minus 30 is 20. So x has to be -20, right? Because I want this to equal 0 over 6 to the 3. So I have x is is it -20? Yeah. So in order for this game to be even, if all 3 rolls result in 6, Simon should pay $20 to Lindsay. And if they do that, Lindsay's only paying $1 at a time, Simon paying more, ostensibly, but on average, they should average out to 0. Okay. All right. There, yes. Questions? Okay, so that's it for today. Yeah, tomorrow I have my office hours at 10, but if I don't see you then, I will see you guys next week.